Good morning, class. I am Utkarsh, international graduate student at UCSD pursuing master's degree majoring in computer engineering. Today I will cover the topic of pipelining hazards. So let me take the case of RISC-V architecture to explain it much more clearly. As we could see, there are basically 5 stages of pipelining in RISC-V architecture. The first stage is the instruction fetch stage from the memory. The second stage is the instruction decode stage and register read, and now the third stage is the execution of those operations and calculation of address if required. The fourth stage is the memory access, and the final and last stage is the result write back to the register that we calculated in the execution state. Now obviously there are certain number of improvements if we consider pipelining, but at the same time we need to consider the situations in which it is not possible to execute the instruction in the next instruction cycle. So today I am going to cover the pipelining hazards, and there are basically 3 major hazards that we are going to consider today. The first is the data hazard. Now data hazard happens due to the dependencies between the two instructions. Let's say if one instruction is going to execute, then it needs to wait for the completion of data access of the previous instruction. Let me give you an example to show this much more clearly. Let's say we have a add instruction which uses 3 register x19, x0 and x1, and then we have a subtract instruction which also uses 3 register x20, then x19 and let's say x4. So the data in the x0 and x1 register are basically added and stored in the x19 register. As we could clearly see, there is a dependency between these two instructions, and the subtraction instruction has to wait to load the result of x19 till it has been executed in the add instruction. Now we could use several techniques to avoid the penalty of data hazard. One such technique is the forwarding or bypassing technique. In this type of technique, let me show you with an example. Let's say if we have a time axis here, we have different times, and then we have add instruction, and basically 5 stages of pipelining: instruction fetch, instruction decode, execute, memory access, and then write back, right? Here, and then we have a subtract instruction in the next instruction cycle, so it will wait for this time, and then again 5 stages of pipelining: fetch, decode, execute, memory and write back. So the latch at the end of the execution stage of addition instruction stores the result of x19, and then it can be directly forwarded to the instruction decode of the subtract instruction without waiting for the whole pipelining to complete and return back to the register. The other technique that we could use is the code reordering, or we could execute them out of order, so that as to avoid the stall in the pipelining and then increase the IPC, or the instruction per cycle count of the processor. The second hazard that we are going to consider today is the control hazard. Now, in this type of hazard, the decision on control action depends again on the previous instruction. Here, branch determines the flow of control, and the instruction being prefaced depends upon the branch condition. For example, there are if and for conditions in C programming language. Let's say if you have if instruction and x equals to 1, then these instructions basically depends upon this particular condition, and execution of them is determined by this condition. Now again we could use a branch predictor in the instruction decode stage of the pipelining so that there is only a stall if there is a wrong prediction being made. For example, again we will go back to the RISC-V architecture. Here the branch predictor predicts the branches not taken, and then those instructions can be prefaced before the branch without any delay. Now finally we consider our third and final hazard, that is structure hazard. The structure hazard happens because there is a conflict of resources being used by the processor. Again, we go back to the RISC-V architecture for single memory only. Here, the load store basically uses data access, and the instruction fetch has to wait for that particular cycle to access the data path. That's the main reason why the pipeline data paths have separate instruction and data memories. So to conclude, basically, data and control hazard are the most prominent hazard that we see in the modern processors. Thank you.